Welcome to Study Loop.
Since we're asked to find the heat exchanged and the internal energy change for three different kinds of thermodynamic processes in this problem, our fundamental approach will be to start from the first law of thermodynamics. So this is that the total change in heat, the total exchange of heat, is equal to the change in internal energy plus the work done. So in part A, we have an isothermal process. This means that the temperature will be constant. We know that if delta T is constant, then the change in internal energy is zero. So this is just T, not delta T, and this is delta U. So the change will be zero. Why? Well, because internal energy will always be proportional to the temperature. So if internal energy changes, then the temperature must change as well, and vice versa, because the temperature is the average value of internal energy per one unit of the structure, one molecule or one atom, depending on the structure. So we know for the isothermal process that the delta U will be zero. Therefore, from the first law of thermodynamics, we know that Q equals W. And since we know the amount of W, we know that here Q equals 300 joules. And this is for the part A. Now for the part B of the problem, we have an adiabatic process. So an adiabatic process is by definition a process, thermodynamic process, where there is no change in heat overall. There is no exchange of heat. It is happening so fast that there is no time to exchange heat. That is the basic presumption for adiabatic process. Therefore, Q equals zero for adiabatic processes. But this implies from the first law of thermodynamics that W plus delta U equals zero. Therefore, delta U equals minus W. And knowing the amount of W, or the work done, we know that the change in internal energy is equal to minus 300 joules. And for the part C of the problem, we also have the process, which is isobaric in nature. So for this kind of process, we can say that the work done is pressure times the constant pressure times the change in volume. And from the ideal gas equation, we know that this can be directly related to the temperature change as nR delta T. And also we can couple N and delta T times R, so that we can say that N times delta T equals W over R, or in this case it equals 300 joules over the gas constant, which is a known value. Also, the heat capacity for an ideal monatomic gas from the textbook is Cv equals 3 over half R, which is very important. Now we can substitute all of this into internal energy expression. So all of this was done in order to have proper forms to substitute into this expression right here. So delta U equals N times Cv times delta T, which when we substitute equals 300 joules over R times 3 halves times R. So this will cancel out. And when we evaluate this, we obtain that delta U equals 450 joules. Now, from the first law of thermodynamics, we know that Q will be delta U plus W, and this equals 450 joules plus 300 joules, and finally we obtain that Q for this process equals 750 joules of energy. And now with this we have completed the whole problem. I hope you find this helpful, and I hope to see you in another lesson.